Hi, welcome to this introduction to VLSI testing in Cadence Virtuoso. We'll be covering the basics of test case generation as well as verification using MATLAB and Verilog A. Let's jump right in. Testing is pretty important in VLSI because it helps us to ensure that the modules we design work as specified. This means things like 8-bit adders can perform addition of 8-bit numbers correctly, and so that when they're used in larger systems, you can trust that they perform correctly as specified. Additionally, the systems that we deal with in VLSI are usually very large, ranging from at least a few bits to hundreds, and that's why it's really hard to test these systems by hand. Imagine iterating through a 64-bit adder even, just running through all these different combinations of inputs by hand. That wouldn't be very easy. This is where automated testing comes in, where we specifically design a test bench to run the tests that we specify and determine that the device under test is performing correctly. A couple of notes on terminology here. A test bench refers to the module that you design to test the module that you want to verify. The module that you want to verify is normally called the device under test, the DUT. A test suite refers to a collection of test cases that you use to verify the correct behavior of the module. With this in mind, we can now take a look at how our simplified testing flow actually works. Typically, we start off by thinking of the test suites that we want to run, and then we build a test bench that will reflect these test suites. For Cadence Virtuoso, we're going to be building our test benches using Verilog A, and we can import them as modules directly to be used. More on this in a moment. After creating our test bench, we then put it in our simulation environment in Virtuoso. Typically, we'll need to buffer the test inputs coming from the test bench that are being fed into the device under test. We can do this using flip-flops. Input buffering allows us to simulate the behavior of the DUT when it's not being fed by an ideal voltage input source such as the test bench. After all, the test bench can supply a fixed voltage at infinite current, and so this is not really realistic, and we want to simulate what it would behave under real conditions, such as when an adder is being fed by a register. After placing our device under test in the simulation environment, we can run the analog simulation. We then place the device under test in our simulation environment and then run the analog simulation. This allows us to collect the waveform data from the device under test and analyze its outputs using MATLAB. We compare these waveforms against a set of gold standard waveforms that we encode into MATLAB. More on this in a bit as well. Now let's consider what it takes to create a test suite that verifies the functionality of a module. For this section, we'll be considering the example of a ripple carry adder. Let's say that you've already created a single bit full adder and you've verified by hand that it works. This is great. All that's left to create a ripple carry adder is to send the carry out bit from the least significant bit to that of the next least significant bit, and so on and so forth until you reach the most significant bit. You may be asking that since you've already verified the single bit's behavior by hand, why do you still need to create a test case that involves the entire adder itself? Well, there are several reasons for this. One is that the overall behavior of the multi-bit adder becomes less simple when you chain up these individual small 1-bit full adders. As you will find in the later analog simulations, timing constraints will play a role in determining the behavior of the overall n-bit adder. Outputs don't rise instantaneously once they change, and these can result in spurious outputs called glitches, and you want to check for that in the testing phase. Verifying the n-bit adder's behavior like this also allows us to make sense of the timing characteristics and the implications this would have on the modules with which it interfaces. So, this is why it's necessary to actually have a test bench that tests the full n-bit adder. But how do we come up with test cases for this overall device? A good place to start is to consider the basic functions of the device under testing, which is, in this case, the ripple carry adder. So, some three basic functions are the sum generation, the carryout generation, and the termination of the ripple carry bit. Once we've arrived at these basic functions, we can then work backwards to find the inputs that would require using these behaviors. For example, for the sum generation, the input of a equals to 1, b equals to 1, and cn equals to 1 gives a sum of 1. However, a equals to 1, b equals to 0, and cn equals to 1 gives a sum of 0. So we can see that the sum bit is actually generated dependent on all three a, b, and cn bits, and we can discover the kind of combinations that will give us the ability to test for this function. The same applies for the other two basic functions, which are the carryout generation and ripple carry termination. Each has a specific set of inputs that allow us to test for it. Remember, the goal here is to aim to test all basic functions of a module. Having looked at all of these different inputs, we can then come up with a list of test cases that can allow us to verify the behavior of this module under different input circumstances. The table shown here is a list of example inputs that I've decided to test the adder with. There's different reasons for why I'm including each row. For example, Test suite 1 allows us to verify the behavior of the adder when both a and b are 0. We also verify for when cn equals to 0 and 1, so that the least significant bit is generated properly. Test suites 2 and 3 allow us to confirm that the adders propagate the carry bit correctly. We have one input that is made up of all 1s, and another input which has 1 shifted by I bit places. The carry bit has to ripple from the ith significant bit to the most significant bit and generate a carryout for this to be a successful verification. Test suite 4 tests a similar case with cn equals to 1. Test suite 5 confirms that the carry bit ripple does terminate properly when the conditions aren't satisfied. In this case, we have one input which has the 4 least significant bits equals to 1. We expect the ripple to stop propagating after the 5th least significant bit. Test suite 6 allows us to confirm that the sum bits for each of the 8-bit places are correctly generated. It also allows us to test the propagation of the ripple carry bit when cn is equal to 1. Now let's dive into understanding Verilog A, which will allow us to program our test bench in Cadence Virtuoso. It's useful to have a working understanding of the different keywords that Verilog A uses. First off, we'll be discussing some of the keywords for analog module specification. These include the module, output, and voltage keywords. The module keyword is what you'd use to initialize a module, which in this case will be the test bench. You specify the module name as well as the pins that it has. The pins are what the module uses to interface with other elements, so this would include both the input and output pins. However, at this stage, you don't necessarily have to specify which are input or output pins. This is just a little bit like the diagram on the right, where we have a part declaration instantiated as well as a set of pins that we're not sure where to place them on the part yet. We can tell Verilog to mark a pin as an output pin by using the output keyword. In the diagram, this is a little bit like attaching previously unspecified pins to the output ports of the part. We can also specify that the output is intended to be a voltage signal, and we can do this using the voltage keyword. Similar to C and C++, Verilog actually has several different ways that you can use to declare variables and constants. In the context of Verilog, some kinds of for loops are known as generate constructs. To declare the counters for these for loops, we need to use the genvar keyword. In those cases, it is advised not to use integer as the variable initializer for the counter. However, we can use integer and real to initialize variables with these corresponding data types for other purposes. We'll be able to see this in the next section of this video, where we go over a code example of how to implement the test bench. Local param and parameter are Verilog keywords that allow us to declare constants, and you may think of these as being similar to the static keyword in Java. There is a key difference between local param and parameter though. Local param refers to private constant values whose scope is the module in which it is declared, while parameter does not have the same scope declaration. Next, we have miscellaneous keywords such as include and define. Include is a keyword that allows us to link to other files and modules for use in the current Verilog file. So some files are included by default when we create a new Verilog A cell view in Cadence Virtuoso, and we should avoid deleting those as it's required by the system. If you're familiar with the concept of macros, the define keyword is what allows us to declare them. Next up, we'll be taking a look at how we actually write the test bench in Verilog A. This is the Verilog A script that we'll be using to create our signal generator, which is our test bench. I've written this signal generator to test an 8-bit adder, so let's dive in. You might note that first up, I'm actually editing this in VS Code, Visual Studio Code, which is a free code editor that provides a lot of great syntax highlighting that editing in Cadence Virtuoso actually may not provide. And there's also this really interesting add-on that you can choose for Visual Studio Code where it allows you to highlight some of the Verilog syntax and perform some of the linting and formatting as well. So this is a really useful extension for VS Code when you're editing Verilog files, and I recommend it. With respect to the files, let's see how it's actually structured. So we start off with the default required files for Cadence Virtuoso. These are the constants and disciplines files. We should not touch this since this is system generated when we're creating a new Verilog A module in Cadence Virtuoso. Next up, I use a macro to define the adder's bit width. So the macro in this case, I'm just substituting n bits to represent the number 8. And so wherever I use it, I'm just representing the number of bits that the adder is actually using. Here I actually start declaring the module for the signal generator. I've named it lab4 signal gen WFF. You can name it whatever you want. And I'm also specifying the pins on this module. So note that at this point, I'm still not specifying whether or not the pins are inputs or outputs as we discussed earlier. And that's where we actually specify it below here. So Cin and clock are actually outputs of this signal generator, which are going to be fed into a buffer stage, which is then driving the inputs to the adders. So the flip-flops act as the buffer. So this is how you declare multi-bit outputs. You can order it from most significant bit to least significant bit. So 8n bits minus 1 is basically 7 to 0. So that's 8 bits from MSB to LSB ordering. Same goes for B. And I also declare that these pins are actually voltage outputs. So this means that they can take on a continuous range of values, and the output we expect from them is a voltage. And here we define some locally scoped constants using the local param keyword for the time periods that we're actually using. CP will represent the clock period for the test cases, while CP2 represents the clock half period for the FF clock signal. The reason for why we're using the clock period versus the half period for this will be shown in a bit when we discuss how we write the flip-flop. So the P suffix actually refers to pico, so this means every 4,000 picoseconds there'll be a complete clock period for a single test case. So here I'm actually defining the number of test cases per test suite, and I'm using the local param keyword. So remember that the local param is actually a local scope constant, and I'm declaring that there's going to be two test cases in test suite TB1, and then 8 test cases in test suite TB2, and so on. Next, I declare a real variable, which is the clock signal. This keeps track of the voltage that we want to output to the clock, and we'll see about how to write to the output pins in a moment. These are the constants that I'm declaring to define the time period over which this signal generator is going to output a signal. So parameter means that it's a constant, and real means that this takes on a real value, and it extends from the time period t equals to 0 to t equals to infinity. So this is going to be a signal generator that keeps generating a signal regularly over this time interval. And I can define the rising edge and falling edge. So this is what defines the time it takes for the signal to rise from low to high, and then to go from high to low. So I'm also defining a few more constants about what the voltage actually is. The high voltage is 1.2 volts and the low voltage is 0 volts. Next up, I initialize some integer variables for signal generator outputs. So because we're creating a test bench to test the 8-bit adder module, we are outputting like a set of integers that will be added to each other, as well as the carry in bit. And this is what stores that information. We'll eventually need to convert this to binary below. And this integer helps keep track of how many test cases are completed. And there's also some helper variables that allow us to switch between the different test cases within each test suite. Here, we initialize a counter for the for loop that we're going to be using soon. Because the for loop in Verilog is considered a generator construct, we cannot simply use integers to count. So we need to use declare j as a gen var to use it as a counter for the for loop. With analog begin, we signal that we're describing the analog behavior of this module. Next up. Okay, so first up, within this analog portion of the script, we actually initialize the signal generator output values with this initial step keyword. And now we come to the timer block. We declare a timer that has a delay of 1 nanosecond and then runs this block of code every clock period 2. Remember, we declared clock period 2 as the half clock period of the flip-flop clock signal. And why it has to be the half clock signal is because of this. So every half period we check whether or not the clock signal is low. If not, we set it to high. And on the other hand, it is high, then we set it to low. So that means that it effectively completes one cycle for every 2 of this clock period 2 variable. And so this is why this is the half clock period. We then write to the output pin using this line right here, using the transition function. So the syntax of it goes like this. Since we're writing to the voltage, we have a V, and we write the voltage of the clock output pin, and then we write it. We have to transition the voltage between the low and high levels to this target value of clock sig, which we've specified earlier. And then we have the rise time and the fall time. Here we actually start defining the test cases that we're going to run. Here we define the timer block as before and then start with our test suites. So we check for whether the current test count, which counts the number of test cases, is less than the number of test cases for the test suite TB1. And then we begin by writing all zeros to all of the inputs to the adder. And then when we increment to the next test case, we then run with the Cn equals to 1. So this constitutes our first test suite right here. And then we repeat a similar process for test suite 2, where we check whether the current test count is within the range of TB2. Then we then we set the different inputs. And this continues for the next few test suites. At the bottom here, this is a pretty important part, which describes how we actually write to the output pins. So this is the generate construct for loop that I was talking about, where we're using the gen var j as the counter. So we iterate from j equals to 0 to j equals to 7 in this for loop. And at each point in time, we take the bitwise end of the integer representation of the input with the 1 bit shifted by that same value of j. If the bitwise AND is equal to 1, then we output a high to that pin. Otherwise, we output a low signal. And then we specify the T rise and T fall as before. Same goes for the output for B. And then for Cin, if the Cin car is the Cin input is high, then we write the voltage high to this Cin pin. Otherwise, we write a voltage of V low to the Cin pin. We make sure to close off any of the function blocks with the AND keyword, and then close off the module with the AND module. We now create the cell view in Cadence Virtuoso. First, we go to our Virtuoso log window and then open up the library manager. We then click on File, New, and then Cell View, which allows us to give a name to our new cell view. We can also set the cell view type to be Verilog A. Once we're done, we press OK, and this opens up a new text editor where we can paste in our code that we just wrote. The first time we press check and save, which is the save button with the check mark on the top left, the Verilog system will ask us to specify a symbol for this new cell view. And we can follow the instructions to create a new symbol with the pins that we've identified in the module. As you can see, Virtuoso recognizes the pins that we've declared and placed them as output pins. The multi-bit output pins, such as A and B, are displayed as such. With the cell view created, we can now set up the simulation environment. This is an example of how I set it up. I connected the signal outputs from the signal generator to a buffer stage for the A, B, and Cin inputs into the adder. The clock output from the signal generator provides the clock signal needed for each of the flip-flops and registers. Also, you can note that this is how you declare multiple bit buses in Cadence Virtuoso using the same MSB to LSB designator that we used in Verilog A. The outputs from the buffer stage feed into the adder shown here, and you can read each of the outputs as such by destructuring the bus. I won't go into the specifics of how to design the adder, but this is in general how you can read the voltage outputs at each of the 8 bits of the adder. And after running the ADEL simulations, we can inspect each of the signal generator outputs and observe the waveforms, which should be similar to those shown here. The waveforms shown here cycle through the different test cases and provide different sets of inputs into the adder. After running our test bench, we export the signals as a PSF file and use the MATLAB code shown here for verification. At the top of the MATLAB code, we first define some parameters used in our test bench, including the number of bits and the delay. We then read each of the output signals from each of the output wires. For wires with multiple bits representing the input-output bits as well as the sum, we concatenate these in a vector. Following that, we convert the analog continuous signal to a digital signal of zeros and ones, and then find the decimal representation of the inputs at each time step. Using this decimal representation at each time step, we can then derive the expected sum as well as the expected cout. We choose a sampling time midway through the period of each test case. At each sampling time, we compare the expected output of the adder against the actual output of the adder. If there are any errors, we log it as shown here, and if there are no errors at all, we will display a message saying that the adder has no errors for all 24 test cases. And there you have it, a simple testing scheme to get started with your VLSI project. And feel free to check out the GitHub links in the description of this video where you can find access to the scripts that we've covered here. Most of all, have fun!